Alright, so here we are with section 2.4. Gonna kick things off with one of your favorite things, polynomial long division. I know it's not one of your favorite things, but you guys did learn this in Algebra 2, so we're gonna go through one of these guys. So first things first, we're gonna set this up just like we would normal long division. So whatever we are dividing by, we are putting on the outside. So we got our 2x squared plus x plus 1. And I'm putting this guy on the inside. So here's one of the things you got to remember on this, and this is why I gave you this problem in particular, is because when you do long division, whatever we got under here must be complete so that we have every term accounted for. So if we are starting with 2x to the fourth, then we must have x to the third behind it. Then we must have x squared, and if they don't have one, we fill it in with a 0. This becomes super helpful with just being a placeholder so that when we go through our process, all of your terms line up with the one that they're supposed to line up with. So we're putting in those placeholders. So after x squared, we're going to have 0x to the first, and then we can put the constant at the end. But every term needs to be accounted for. So as we go through this, remember it's just long division as usual. The same steps that you took with regular long division, like way back in like 4th grade when you learned this, apply to this. So first thing starts out with division. The best way to look at this, as you were probably told last year, is instead of saying how many times can this go into this, the better way of saying that is if you just look at the first terms, what would I multiply times 2x squared in order to get 2x to the fourth? Right, and that answer, which is x squared, goes up top. So whenever you take that division step, that's where your answer comes from. Step 2 would be to take whatever you get, multiply it times your divisor. So we're going to take x squared and distribute it to all 3 of those terms. So times our first guy would give us 2x to the fourth. And your first term should always be the same if you did this right. X squared times x gives you x to the third. And then x squared times 1 gives you your 2x. And this is why, 2x squared, x squared. But this is why you have those placeholders, right, so that we're lining up our terms based on exponents. So that's why that's there. So after you multiply, step 3 is to subtract. So we're going to subtract straight on down. These guys will cancel if you did this right. So I'm looking at negative x to the third minus 1x to the third, which will give me negative 2x to the third. And then 0x squared minus x squared would give you a negative x squared. And those are the 3 main steps. Beyond that, it's just bring down and repeat. So we're going to bring down our next term, which is just our placeholder of 0x, and then we're going to repeat our process. So now we're back to looking at just the first terms, and I would say, what would I multiply times this in order to get this, right? And you can see I would multiply by negative x. So that's what goes up top. So I need to take my negative 1x, distribute it to my divisor. That's your divisor. That's your dividend. This is our quotient, the answer. So we're going to take that negative 1x times all 3 of those. So negative 2x squared. Negative 2x to the third. And those guys should always match up if we did that right. Negative x times x would give me negative x squared. And negative x times 1 gives me negative 1x. We subtract. You do have to be careful on the subtraction step. This is usually where the mistakes get made, is right here where you subtract. One thing that would help, as your Algebra 1 teacher probably taught you a long time ago, is anytime you subtract polynomials, instead of subtracting, it's often better to change that to a plus and change all of the signs behind it, right? So the whole add a line, change the sign thing, if your teacher told you that one. So we're going to change that to a plus, and that changes everything behind it. So you become plus, plus, plus. Now it's just addition, and addition is generally safer than subtraction in terms of mistakes. So these guys still cancel just like they're always supposed to. These guys cancel. These, when I add them together, just gives me x. As I bring down my final term, we can see that there's nothing I could multiply times this in order to get this, because x to the first is smaller than 2x squared. So that means we're done. It means whatever is left is your remainder. So how do we write the remainder with long division? If you guys remember, whatever is left, we put a plus, and we put the remainder over the divisor. This is the way that you would have written your answers last year, and we're still going to be doing that, but there is another form that they do want you to be aware of. What we just wrote, obviously it has a fraction, they call that fraction form, but there is another form called polynomial form on page 193. Let me show you what that looks like. So here's the answer that we just got, is right here. This is the other type of answer. So this is called polynomial form. So what they do is they take the divisor, so that's first. They have the quotient, which is second, and then you are adding the remainder at the end. Here's why they write it that way. As far as the setup goes, this is the original problem that they gave us to start with, right? So this was, I wrote it out sideways as this divided by this, but you could write it out in fraction form as well. But if we did that, here's what it equaled. So if you just look at this as sort of one big equation, you'll notice this denominator and this denominator are the same. So if I were to multiply this entire equation by 2x squared plus x plus 1, and I distribute it to this, and to this, we would end up with this look right here. So it all means the same thing. It's just two different formats for the way you would write your answer. So anyway, just at least understand that these both mean the same thing. And so if we're asked for something in fraction form, it should look like this. Sort of a polynomial form would be written this way. Okay, let me take you back to our notes. There is a remainder theorem. This is also an Algebra 2 concept that you would have received last year. But if our function is divided by this, so this is what's on the outside, this is our divisor, then the remainder, which we're calling r, is equal to f of k, whatever this is. Okay, so let me give you a simpler look at that. I like to show you what the theorem is, but here's what it means. So let me show it to you this way so you can see this. And you're obviously seeing a pretty big connection here to Algebra 2 from what you did last year, but don't worry, this will progress. These first chunk of notes are sort of review so that we can progress into some other things that you wouldn't have done last year. So anyway, so if we have this is our f of x. It is, if it was divided by x minus 3, so from what I just showed you on the last page, so this is f of x, this is x minus k, right? That's what we're looking at. What they're saying is the remainder that you're going to get from this, if you were to do long division, whatever you have left is the same thing as if you were to just plug in positive 3 in for x. Right, that result would be the same result that you would get in the long division process. Okay, and I'm going to show you as we go through this guy right here, so you can kind of see all this put together. Keep in mind that if you have no remainder, right, that means whatever you were dividing by went in evenly, right? If there was nothing left over. So if you have, so take a look at this one. So when they divided this guy by x minus 1, you'll notice there was nothing left over. So, and you could find that out in two ways. One would be to use long division like we just went through. The other way would be to take positive 1, plug it in for x, that's what they did here, to see what the remainder was. So if you get a remainder of 0, that means this went in evenly, which means x minus 1 is a factor of this. So if I were to factor this and put this in factored form, this would be one of those factors. Okay, let's go through one of these guys. We're going to do a little synthetic division. Put a couple ideas together here. So keep in mind that if I were to plug in positive 3 in for this, I would get the remainder. And if that remainder were 0, that would tell me that x minus 3 is a factor of this polynomial. Right? So that's one of the things we're going to be looking for moving forward. So synthetic division, also in Algebra 2. So you could set this up with long division and use x minus 3 as your divisor. This is your dividend, meaning it goes under the fraction bar. And you could go through that process. There's nothing wrong with it, but synthetic division will get you there quicker. Here's the only catch. Synthetic division only works when this is in its most basic form. It has to just be x plus a number or x minus a number. This will not have exponents, so you can't do this if this were x squared. You can't do it with any higher order other than just x to the first plus or minus a number, right? So it's got to look like this. When we have this scenario, we take the opposite, so positive 3. We're going to put it in the box, and I guarantee this will look familiar to you if it doesn't already. We're going to take the coefficients of all 4 terms. So my first term's coefficient is a 2, then a negative 3, then a negative 5, then a negative 12. Do keep in mind that I would fill any of these in with zeros if we were missing a term. So just say, for example, the minus 5x was not there. Like, let's just say the original problem was 2x to the third minus 3x squared minus 12. And that was the original problem. I would have needed to put a 0 here as a placeholder to fill in that space. So make sure all our terms are accounted for. This one is good. It's 3, 2, 1, and then your constant. So we're safe. So the 2 steps of synthetic division. And we always start this by just bringing down the first term. So we bring down the first term. The 2 steps are multiply and add, multiply and add, multiply and add. So we do 3 times 2. That number goes here. And then we add straight down. And we just keep repeating that process. So 3 times 3, that number goes here. We add straight down. 3 times 4, that number goes here. We add straight down. Voila, we got a 0, which means that's our 0 remainder. So x minus 3 is a factor of this polynomial, which also means that if I were to take positive 3 and plug it in for all of those x's, when I simplify it, I would get 0. Right? That's what that theorem was telling us just a minute ago. Just to kind of finish this one off, remember how synthetic division worked. It's kind of like you took out the x's to do the problem, but then you got to put the x's back in to show your answer. It's always one less exponent than what you started with, right? Because we divided. So it's like we took out an x, so here's what's left. So we started out with x to the third. So this, in our answer, we would now have x squared plus x to the first plus our constant, and then that guy at the end represents our remainder. So let me kind of piece these together for you. That means if I were to multiply 2x squared plus 3x plus 4 times this guy times my divisor, it would equal that polynomial. So if we're giving this polynomial and it just says, hey, we want you to factor this or break it down into parts, this is now the 2 factors that make up this polynomial when we put together this guy. So hopefully that helps. I'm always happy to take questions on that if we run into some issues. Okay, so if we are given a polynomial function like this and we are looking for the rational zeros, keep in mind when they say the zeros, that is synonymous with x-intercepts. So if I were to graph it, or if I'm able to look at the graph, I can tell by looking at the graph there are 3 zeros, right, to a function like this. So a couple theorems you guys would have picked up last year would be that whatever your degree of your function is, so like if this is x to the third, that's my highest power, that means there can be at most 3 rational zeros, right? So you got 3 x-intercepts potentially. There could be less, but there cannot be more. If there are less showing, that would mean, and this is where we got into a little bit of the imaginary number stuff last year, if they're not real zeros, then they would have to be non-real or imaginary zeros. So if you had a graph of like x to the third, what that would mean is, and don't draw this because this is not an accurate graph, but like let's just say it looked like this. So if that was my x to the third graph, I know if it's x to the third, there are 3 solutions, right? 3 zeros. But according to the graph, I only see one of them on the graph. So if there's one real zero, that means the other 2 are non-real zeros, right? Or 2 imaginary zeros is kind of what happens there. So anyway, the other theorem is, how do we start identifying what the possible rational zeros are? So as I look at this, and you can see this theorem on page 196, but to be honest, they throw in so many symbols and stuff that it doesn't always make that great a sense. So I'm going to try to put it into some plainer English for you. And this is a better way of looking at it right here anyway. So when I have this function, they call this, the one at the end, your constant, they call your p term. So that's p. The leading coefficient is your q term. And so the issue is, if I took all of the factors of p and divided it by all of the factors of q, that would create my list of possible rational zeros. So we call this p over q. So if you look at -1, and this could be positive or negative, we actually have to consider all of them. That's why you see all these pluses and minuses right here. So it doesn't matter if this says plus or minus, we still put plus or minus in front of all of our stuff. So this one's super simple because what are the factors of 1? Well, 1. That's the only factor of 1. Factors of 2 are only 1 and 2, right? So here's all my factors of p. This is all of my factors of q. So what are the possible rational zeros? It could be 1 over 1 or 1 over 2. It could be -1 over 1 or -1 over 2. And that's really it. So it was like the positive or the negative version of each one of those combinations. So why do we do that? Because when I go to start doing my synthetic division and I'm trying to figure out where my zeros are, I don't want to have to play with too many numbers here. I want to narrow down my list of options. So if this is my list of options, then when I go to decide what number I want to put in the box, I'm going to choose from this list, right? So like let's just say I tried 1 and I didn't get a 0. And I'm like, okay, well, let's try something else. So then I would try -1. Well, what if I don't get a 0? So then I got to try something else. Well, this tells me what I should try next. I would have to put 1/2 in the box. I wouldn't go to 2 or -2 or 3 or -3 because they're not in my list, so I'm not going to even try them, right? So this is a way of trying to narrow down the process of what you're going to use here in order to come up with your zeros. So that's what this is for. It's just there as a way of helping. What we're going to do, and this is what I wrote down at the bottom, to help sort of narrow down this process, we're going to use our graphing calculator and make a graph like this one. So to help us see where our zeros are, right? So if you look at this, I can see that I have a 0 at -1, -1/2, and +1. And you'll notice all three of those are in my list right there. Here's what I wrote down here, and this is super important, so I hope you hear me closely on what I'm about to tell you. This looks like -1/2, right? Well, what if it's not? What if it was an irrational number? Because that's possible. This list that you see right here, these are possible rational zeros, right? Well, that doesn't mean you can't get irrational zeros. You can have irrational numbers that will also potentially give you your zeros to be your x-intercepts. So here's what I ask. If I was looking at this graph, here's kind of the way we would approach this problem. First thing I'm going to do is I'm going to take this and I'm going to graph it. Then I'm going to list my possible rational zeros. The third step would be, okay, whatever I see on here, so it looks like -1, yep, it's in my list, so I'm going to put -1 in the box and see if it gives me a 0. All right, that's going to be the process. We're not just going to go off of the graph. Okay, this is still necessary. You have to do this with each of your answers to test them and see if, in fact, they are zeros of your function. Okay, because it's still possible to get irrational numbers that would not be in your list, but they would show up on a graph, if that makes sense. So if not, please ask and I will clarify. But again, all that is to say you still got to do the synthetic division with your answers that you're getting from the graph to make sure that they really are the answers that you think they are. All right. So here's what we got. In order to put this into factored form, remember they put +1 in the box, which means, and it gave them a 0, which means x minus 1 is a factor. Here's what was left. So then they took this and factored him one more time to get this. So there's two ways you could have done that. You could actually just do basic trinomial factoring to get these factors, or if you would try synthetic division with -1 and it worked, well then that means now I can write x plus 1 as a factor, and this is what would have been left over in my synthetic division process. So you can use synthetic division, that works. But we could also do it by just sort of basic trinomial factoring once you get to the quadratic stage, like this one is. Okay, let's try something. So we're going to try number 9, and we're going to go through the process that I was describing on the last page so that you can kind of see how all this goes from start to finish. And this will be the last thing that we do, so stay with me. We'll get to part 2 in the next video. But I want to make sure we go through one of these from start to finish together so you can see how all this goes. So I put in, let's see, I put an extra page on here for you. So this was example 5, number 9. I wrote that 2 pages later, right here, so that we could do it on this page for practice. So this is what it looked like. So we're going to start out by, we're going to graph it in your calculator. We're also going to list our potential rational zeros. So we're going to start with our P over Q. So every factor of 1 divided by every factor of 2. And this will be just like the last one that we did. They can be bigger than this, but I just want to get through the process here with you at once. So it's every factor of 1 over every factor of 2. So every factor of 1 is plus or minus 1. Every factor of 2 is 1 and 2. So here's what that would look like, and then we're basically distributing. I'm going to do this over this and this over this, right, to come up with my complete list. So positive 1 over 1, negative 1 over 1, and then I got my 1/2 and negative 1/2. So there are 4 possible rational zeros for this function. And so we're going to start by using our graphing calculator and graph this. So if you take a look at the function here that we're putting in, so I wrote something important in here, and this is kind of what I was talking about earlier. This is an x to the 4th, which means I'm expecting 4 zeros right? 4 solutions. However, they could be rational, they could be irrational, or I might only have 2 real solutions and 2 non-real solutions. So there can be all these different variations of where those 4 answers are coming from. So it's kind of important that we sort of check in a few different ways, and that's why we're going to use synthetic division, we're going to use the graphing, we're going to sort of use all of our tools to make sure that we're accounting for our possible answers. This is one that always messes with people too, right? What if you had identical factors? So if I had something like this is not part of the current problem. I just wrote this in as an example. But what if like my 2 factors were x minus 3, x minus 3, right? Well, technically they count that as 2 solutions, even though they're the same solution. So on a graph, you wouldn't even know that. It would be like looking at this and you'd say, oh man, it's the same factor twice. So even though my solution is 3, it counts for 2 different solutions, right? Because there's a multiplicity of 2 there. So anyway, let's take a look at the graph. Here's what it should look like for you. So I can see 2 real zeros, and it looks like I have one at -1/2, and it looks like the other one is +1. So to me, it looks like I'm getting this guy and this guy. So now we want to test using synthetic division to see if those are correct. So I'm going to take +1, put it in the box. I'm going to bring down my coefficients, which were 2, -1, +1, -1, -1. Right, so we're going to test this, see if we get a 0 remainder. We're going to bring down that first term. I would have filled in zeros if I needed placeholders, but every term was accounted for. So we're just to the 2 steps of multiply and add. So 1 times 2, and then we add straight down. We're going to do 1 times 1, add straight down, 1 times 2, add, multiply, and add. And sure enough, we were right. That was one of our intercepts on the graph. Here's what's left. So kind of a couple things we could do now. Let's take the remaining values. So I'm going to bring down the 2, 1, 2, 1. And I'm going to try synthetic division with the other guy that I suspected as my other 0. So I'm going to put -1/2 in the box. Bring down my first term. And repeat that process. So 2 times -1/2 would be -1. Add those up. 0, add those up. -1, add those up. And sure enough, that was our other 0. So this is what's left, right? So I'm left with, and remember, it's one less than what you started with. We started with x to the 4th. This process brought it down to x to the 3rd. This process brought it down to x squared. And so I am left with 2x squared plus 0x plus 2. And so this is what we have left. So here's what I wanted to show you. What we were talking about earlier, where I remember for this problem, we were expecting 4 zeros. We've only found 2 of them. 1 and -1/2. And even when we looked at the graph, it appeared that there was only 2 real zeros. The multiplicity thing, if you think back to our last lesson, I know neither one of these are duplicate answers because the graph crosses the x-axis instead of bouncing off of it, right? If it bounces off of one of your intercepts, then you know that's a repeated answer, right? Like a x squared type of an answer. But if it crosses through, then there's only one of them, right? So that means as I look at this, I have 2 real zeros. The other 2 must be non-real zeros. So if you get a problem that asked you to find the zeros, those 2 guys would be your answers. If you had a problem that said find the factors, well, here's what would be our factors. So that's one of our factors. X minus 1 is a factor. And x plus 1/2 is a factor, which could also be written as 2x plus 1. So whenever you have a factor like this, if you want to put it in sort of the normal factored form that we would put it in where there's no fractions, that means the bottom number goes in front of x. So this same factor could also be written as 2x plus 1. And let me show you why, because this sort of leads me to the final thing I wanted to tell you. If you had a question that said find all of the real zeros, well, here you go. But if you had a question that said just find all the zeros, meaning real or non-real, well, how do we always find those? We take our factors, we set them equal to 0, and we solve for x. So if I set this equal to 0 and solve for x, I would get negative 1/2. If I set this equal to 0 and solve for x, I would get negative 1/2 again. So that means whether I write it this way or this way, they really mean the same thing. Okay? So that would give me one of my zeros. If I set this equal to 0, then x equals 1 would give me my other 0. Well, where are the other two zeros? What if we set this equal to 0? So if I set 2x squared plus 2 equal to 0 and solved it, so subtract your 2, divide by 2, square root, and look at what we got. We have non-real, or what you could say imaginary solutions, right? These would be imaginary solutions, and there's two of them because we always put the plus or minus in front whenever we do this. So to put it all together, there are 4 solutions, but 2 of them are real and the other 2 are non-real. So just make sure with whatever the question is asking you for, that's what you respond with, because they might ask you for factors, they might ask you for real zeros, they could ask you for non-real zeros. So we just have to read careful for what the question is asking for.